Alright, so in this video we're going to go through the full lateral controller design for the basically the pitch and the yaw autopilot based on the XFLR plane. So this one's probably going to be a long one, but we'll get through it as fast as we can. I think the overall design methodology I'm going to do is go through the development of a full 6-DOF model in Simulink, and then we're going to tune the controllers around that full 6-DOF model. The other option I was playing around with was doing a nonlinear lateral model, similar to what we did for the pitch design, but I figured it might be easier and a little bit more informative for you guys to just go through the full 6-DOF model development. So let's go ahead and get started. I'm going to open up XFLR. We're going to look at the plane we did last time. We're going to have to do some new analyses, looking at some of the sort of the beta sweeps and looking at the lateral dynamic response. So let's open up our plane from last time. And if we look at the configurations we have a negative, a neutral, and a positive configuration. So these are all for the elevator. What we need to do now is we need to create positive and negative configurations for the rudder. So we're not going to do the combinations of like negative elevator, negative rudder. We're just going to kind of assume some superposition and we'll add them together. We'll only look at the rudder and beta for the lateral coefficients, and I think that'll probably be okay. So I'm going to duplicate this plane design. So current plane, duplicate. We're going to call this positive yaw. So positive is going to be a positive rudder deflection is going to be the trailing edge to the left. We've got that, and we're going to go right click, current plane, we're going to edit the plane, and what we need to do is we need to replace the fin with not our NACA neutral one, but we want the one that's, which one is it? It's either going to be the down or the up. We'll try the down first. We want the trailing edge to go to the left. Alright, so we guessed right. So we've got that now. We have a neutral elevator position, but we have the adjusted rudder position. So we can go to analysis, define an analysis, and this time we're going to do type 5, which is a beta range. This is going to be a beta sweep, and we want to do this beta sweep at the angle of attack that's going to correspond to our glide condition. So for this particular design, that occurred around 4 degrees alpha, and then I'm doing the 30 feet per second still. Under analysis, I'm going to go through these tabs, make sure everything looks right. The reference dimensions, again, we want to change it to the wing plan form, not the plan form projected onto the XY plane, but the plan form. And I think that should do it for us. So go ahead and hit OK. And I'm going to run beta -5 to 5. All right, so I was able to run successfully. And I can kind of look at the different beta ranges to look at the pressure distributions. And then also, if I go to the graphs, let's see, this one? No. This one, I think, yeah. So I've changed the I've changed what's being displayed. So to do that again, you just right click. Where is it? Current graph, define graph settings, and you can choose what you want to plot. So what I'm looking at now is I'm looking at CY, side force coefficient, CL, and CN. So C little l, C little n. So side force coefficient, rolling moment, and yawing moment. Okay. So the other thing we want to do is we want to run the same yaw analysis on the neutral configuration, because right now this has the positive yaw, the trailing edge to the left, which is going to generate positive side force like we'd expect, a negative yawing moment, so that looks good, and then the rolling moment is pretty darn small. So let's go ahead, let's go back to our neutral configuration, and we're going to do that same analysis. So define an analysis, it's going to be that type 5. That looks good. 30 feet per second, 4 degrees angle of attack. Okay. Then we're going to run that same -5 to 5. All right. So now we'll have a new curve. So we see this one right at 0 beta has 0 side force like we'd expect, and 0 rolling moment, 0 pitching, or 0 yawing moment, sorry. And then we're going to run one more. So I'm going to go back to the plane, I'm going to duplicate this, and then this one is going to be called negative yaw. And then we're going to edit the plane, edit the fin, and I'm going to change it to the up version. Save that. All right, so now we have the trailing edge to the right. And then we can run our same stability or our same analysis, define an analysis. Everything stays the same. Hit OK. Analyze. Okay. So now we have for our lateral coefficients, we have both the kind of neutral configuration, the rudder to the left and the rudder to the right. So if we look at our plots, we can see the appropriate curves here. So from a stability standpoint, we have a positive CN beta, which is good for static stability, and we have a negative CL beta. So that all looks good. I think the next thing we want to do is go ahead and export these polars. So I'm going to go to polar, current polar. Where is it? How do I do this? Oh, there it is. Polars, export all polars. So I'm going to just use that folder again. And then now, if we browse to that location, we should have a few more now. We're going to have our negative yaw, our positive yaw, and then our neutral. So we also have a neutral. This one right here, this is for the longitudinal analysis we did. So this is looking at your longitudinal coefficients. The positive without anything else and the negative without anything else are also those longitudinal coefficients. So let's go ahead and let's make a new spreadsheet. That's going to be our lateral arrow data. We'll open this up. Okay, so I've got the lateral data open here. It's just a blank spreadsheet. I'm also going to look at what we have for our individual data files. So if I open up the negative yaw, see we've got alpha, beta, and then the ones we're going to be interested in are going to be CY, C little l, C little n. So let's see. I know I'm going to have beta, rudder, and then CY, CL, and CN. So let's go ahead. I know our first one, we're going to have -10, and then beta, I'll go ahead and copy it from the negative yaw here. So beta is going to go -5 to 5, and then we're going to have CY, CL, CN, and then this is all going to be -10. And then we're going to have 0. Oops. And then finally 10. All right, so let's go pull the 0 data, which is going to be our neutral one. That's the T5, the type 5. CY, CL, and CN. And then finally the positive. Alright, so this should be everything we need for our lateral coefficients. Yeah, I'm just doing some spot checks here. So I'm checking, if you look at the yawing moment, when we have -10, that's going to be trailing edge to the right. We have a positive yawing moment. And then when it's a +10, that's trailing edge to the left. That's going to give us the negative yawing moment. I think that makes sense. And then for CY, when we're at -10, that's trailing edge to the right. So it's going to be a negative side force for most of them. And then a positive side force for the opposite. So I think we got all that looking good. I'm going to close that, close this guy, and let's go into MATLAB now. We'll go ahead and import that data and get it saved in our ArrowMat file. Okay, so I'm gonna go to where all that is. And let's go ahead and import the existing arrow data we have. Then I'm gonna also import the, let's see, I'll do the negative yaw first, just by double clicking on that. No, we don't want to do that. What am I talking about? We want to import the lateral area data. Okay, and I'm just gonna rename this beta rudder CYCLCN, import selected. So then, similar to what we did last time, I know beta, I'm just going to grab the unique elements there. Same thing for rudder. And then we're going to reshape. So beta is changing fastest, so CY is going to be reshaped, CY length beta length rudder. And then same thing for C little l and CN. So now let's plot all of these. So I'm going to plot beta and CY. I think that makes sense. So in general, as you go to a positive side slip angle, let's see, yeah, that should be right around 0. As you go to a positive side slip angle, you're going to get a negative side force coefficient, since the relative one is going to be on the right-hand side. And then I think this also tracks with our control surface deflections as well. So the blue one, this is going to be the negative, which is the, let's see, the negative is going to be the trailing edge to the right, which is going to generate a negative side force. Okay, yeah, I've convinced myself. I like that one. Let's look at the rolling moment. So we see the negative slope like we saw before, with the negative rudder deflection being a little bit more positive than the positive. So I'm just going to double check that real quick. So here, this line is a little bit more positive, and that corresponds to our negative yaw. So I think that looks good. And then I'll plot CN. So you have the positive slope like we saw before, and a positive rudder deflection should give us a negative yawing moment. But the first one is negative. So the first one is the negative rudder deflection, which is the blue one, and then the positive would be the yellow one here. So the positive rudder deflection, trailing edge to the left, generates a more negative yawing moment. All right. It's so easy to lose track of all the signs and everything. So I think that all looks good. Now there's a few other things that we're going to need to include in our model. So I'm also going to go ahead, I'm going to take that data, I'm going to save it back in that mat file. So that was C little l, C little n, and CY. So we'll throw those back in there. I'm also going to define, we need to know, just in general, we're going to need to know gravity. So make that 32.174 feet per second squared. We're also going to need to know our reference span, so that's B. If we go back to our plane, let's see. So wingspan here is 48 inches. So 48 over 12. So there's gonna be 4-foot span. So I'll save those two real quick, G and B. What else do we need to know? Oh, we also need to save our rudder and beta vectors. We're also going to need updated moments of inertia. So we need IXX. So we can go here. We can go back to the plane editor, plane inertia. We can see IXX is 0.14893. 14893, and that is pound mass feet squared, so we need to get that to slug feet squared, so we'll divide by gravity. And then we also need IZZ for this design as well, which is going to be the 0.35765, 0.35765, 756. Divide by G again, and that G is just to go from pounds to slugs, so you're divided by gravity. So I'm going to add in IZZ and IXX. that might be it for the mass properties. We're also going to need to add in our damping derivatives, just like before. So to do that, I'm going to go back to our neutral configuration, and I'm going to run, this is just like the previous video, that part 2 to the pitch autopilot design. I'm going to define a stability analysis. No, that's not what I want. Analysis, define a stability analysis. There we go. No, that's the same thing. What am I looking at? I guess that's right. Confusing myself. Okay. Yeah, I think we just leave all this as default. So we have the reference dimension set as the link plan form. We're going to do default analysis. Let's hit OK. Just going to overwrite what I've done previously. And I'm not going to run the sequence. I'm just going to run the single point at 0. Analyze. And then let's just do this. Let's visualize it again. So animate, restart. So let's look at the longitudinal. So I remember these numbers from before. That's still looking pretty good. And if we go and look at the lateral modes, so this first one is going to be our roll subsidence. And then 2 and 3 are going to be the Dutch roll modes. And then 4 is going to be our spiral mode. So I think that all looks good. So we're going to just hit L to view that log file. And then we're going to pull out for, like before, we're going to need CMQ for our pitch damping, but also the Dutch roll mode is very dependent on what your lateral damping derivatives are. So we're going to pull out a few of those as well. So let's go ahead and get CMQ first. So we're going to say CMQ is going to be equal to this. It's pi divided by 180, because we want to go from per radian per second to per degree per second, since we're going to feed back the body rates in degrees per second. And then we're also going to look at the roll rate, yaw rate contribution to your rolling moment and yawing moment. So we're going to look at CLP. So that's right here. CLN. Let's see. Oh, not CLN. What am I talking about? CLR. So rolling moment due to yaw rate. And then CNP. Yawing moment due to roll rate. And then CNR, yawing moment due to yaw rate. Okay, so let's go ahead and add those into that mat file as well. So CLP, CLR, CMQ, CNP, CNR. I think that might do it. So I think we're good to, unless I'm forgetting something, which is very possible. We'll figure it out when we get errors. But I think now we're going to be good to go for starting to develop our 6-off plant model. So this will be both the longitudinal and lateral dynamics in this. So let's make a new model. Call this full plant. And let's just start with the arrow. So I'm going to break up the arrow into longitudinal and lateral arrow. So let's go ahead for the longitudinal. We know we're going to need to look at angle of attack and elevator deflection. So let's pull up a couple pre-lookups. This one is going to be alpha. It's going to be our alpha breakpoints. Linear extrapolation. That looks good. And then this is going to be our elevator breakpoints. And we're going to need to do some interpolation here. getting things lined up. There we go. So this is going to be CL. And we'll hook that one up as well. And then we're going to need to have CD. CM. And then we're also going to need to look at our pitch rate damping. So for that, we're going to include our body rates. And we're going to only look at the second one, because that's going to be our pitch rate. So I'm going to do a selector. The input size is going to be 3, which is right, and the index is just going to be 2. Let's hook that up. So that's going to be our pitch rate. We're going to take that, multiply that by CMQ, which is going to be our pitch rate damping. And then that's going to get multiplied by our non-dimensional pitch rate. So to get that, we're going to do C over 2V, just like before. So that'll be C. We're also going to need to include our velocity. Multiply that by 2. Throw in a divide block. Alright, so we have C over 2V times our pitch rate times CMQ. I think that's looking pretty good. Clean this up a little bit. Okay. And then that's going to be added with our normal pitch rate lookup, or I'm sorry, normal pitching moment coefficient lookup. So this one's a function of angle of attack and elevator, and we're going to add in the contribution to damping. And then we're just going to go ahead and output all of these. So this is going to be CL, CD, and CM. All right, I like that. Let's see if this will compile. So far, so good. So I'm going to take all of that, just Control A. I'm going to throw it in a subsystem, and that subsystem is going to be called longitudinal arrow. So now we need to do the lateral arrow. So I'm going to take this, Control click and drag to duplicate it. We're going to call this one lateral arrow. And let's go take a look. So a lot of the structure is going to be the same. Instead of alpha, we're going to have beta. Instead of elevator, we're going to have rudder. We need to adjust those breakpoint vectors. So it's going to be rudder now. And then the first one we're going to have is CY. And then C little l, rolling moment coefficient. And C little r. Or I'm sorry, C little n, yawing moment coefficient. All right. CL, CN, CY. Okay. And this is going to be CY. This will be C little l. This is C little n. Now, our damping is going to be a little bit more complicated this time. So I'm going to go ahead and get rid of this, scoot this over here, and then add another sunblock up here. So we're going to add in both the rolling moment and yawing moment contributions from our damping. So instead of just selecting Q, what I'm going to do is I'm going to make a matrix that has our derivatives. I'm going to take that matrix, multiply it by our angular rate vector, and then use that to be able to generate the rolling and yawing contributions. So let's get rid of this. Get rid of that. These are going to be B now. So instead of like non-dimensionalizing by the chord, it's going to be non-dimensionalized by the span, since these are the lateral terms. Keep the 2. So we'll have B over 2V. That's going to be our non-dimensional roll rate and yaw rate. So let's do a product. This needs to be a matrix multiply now. Bring this over here. Make it constant. And this is going to have our matrix. So this is going to be, the first row is going to get multiplied by each of the angular rates to create the total contribution to rolling moment. So the first one's going to be a roll rate, so that's going to be CLP, and then nothing for our pitch rate, and then finally CLR. So that's going to be our rolling moment coefficient due to yaw rate. And then the next row is going to be CNP 0 CNR. So the same sort of thing. Now we're looking at CN for yaw rate, and we're looking at the contribution from our roll rate and our yaw rate going into our yawing moment coefficient. So we'll take this and we'll go ahead and multiply that. Okay. So I think that's looking good. We're going to need to demux this because right now this is going to be both our rolling moment coefficient and our yawing moment coefficient. So we'll demux that into 2, and then we'll add the individual contributions to each. Can move this a little bit. So the first one's going to be rolling moment, so that'll go up there, and then yawing moment. Yeah, I think that looks pretty good. So I'm going to compile it again just to make sure we don't have any issues. Okay. I think the issue we're going to run into right now is it doesn't know how big this rates signal is going to be, but once we hook this up to our actual output, it'll know, hey, it's a 3-element vector, and then that'll make all the, I think that'll make all these go away. Let's see, is that the only one? I think that'll be fine. We might put it, just go ahead and double click on this and double click on the rates input, set the signal attributes for dimension 3, maybe? Yeah, so if we did that, then it's all fine. We got lots of warnings. That's just because things aren't connected. Okay, so all I did there was I just double clicked on this rates input. I went to signal attributes and said, hey, this is going to be a 3-element vector. So when you go and do this matrix multiplication, everything should work out fine. So now we have our longitudinal and our lateral arrow. So let's go ahead and build up the rest of this. So like before, we're going to need an input for our altitude. And we're going to use that to feed an atmosphere model. We're going to use the COESA. It's the committee on the extension to the standard atmosphere. Switch this to English. So metric to English, get rid of the warnings. All right, we'll hook that up. So the only thing we're really gonna need is density. So I'm gonna throw terminators on the rest of these just to avoid any warnings. And then I'm gonna put in a dynamic pressure block. Hook up density. Then we need our velocity to be input here. This is going to be v, scalar velocity. And the input to the dynamic pressure block for velocity is expecting the basically a three-element vector, body velocity in the body axes. So just to fool it, I'm going to multiply it by 1, 0, 0. So that'll take the scalar and give us a vector. Multiply that there. All right, so now we're going to have our dynamic pressure. And now, let's see. we need to also add in the span and chord factors here. So I'm gonna mux all three of these together. That way we only have one dynamic pressure multiplication. Or one for lateral, one for longitudinal. Hook those up, and again now it's just I click this block, hold control, click the next block, that'll hook up all the like inputs, and then we also just need to realize that CM also needs to have that additional C factor here. Alright, and we're gonna do the same exact thing for our lateral coefficients, only this time both CL and CN need to have a B as opposed to a C. So then let's take these both, multiply by S. So we'll have QSCD, QSCL, and then QSC bar, CM, and then QSCY, QSBCL, and then QSBCN. A lot of stuff. All right. So the last thing we need to do here is we need to do our multiplication with dynamic pressure. And then finally, we're going to demux these so that we can output all of the individual forces and moments. So I'm going to go out one. I'm just going to come up all real quick and then rename them. Okay, so this is going to be lift, drag, pitching moment, and then side force, rolling. Can't do that, so I'm going to call roll for a second. We'll fix this in a second. It's just going to complain if I try to call it L, because it's going to say, hey, you've already got an L. And then N. But if you recall from the last time we did this exercise, the 6DOF model that we're using needs to have basically X be positive out the nose, Y be positive out the right wing, and then Z be positive down. Whereas right now, lift and drag are going to be the opposite directions we're looking for. So we're just going to go ahead and invert the sign here. So then now this is going to become X, still in the wind axes, or still in the stability axes in this case. But it's going to line up with what the forces and moments are expected to be for the wind axes 6DOF model we're going to use. And then, I'm sorry, this should be Z, not X. Z would be opposite lift, and then drag is going to be X now. Oh, we've got that. So I think we've got all these signs. Let's go ahead and try to compile. Still looking good. And I'm going to adjust the order. So we're going to, first one output is going to be X, and then Y, Z, L, which is this. I'm going to rename L. Before, M, N. Okay, cool. I think that all looks good. So I'm just going to, oh, we also need to create our inputs again. So we know we're going to have, let's see, angle of attack, elevator, our rates, and we already have an input for the velocity, so I'm just going to go ahead and duplicate that input here. We're going to have an in for beta, the rudder, we already have a rates input, so I'm going to duplicate that, and we already have a velocity input. I'm going to duplicate that as well. I'm also going to adjust the order of the inputs here. So the first one, I'm going to make velocity. And then the second one I'll keep as altitude. Third, I want to make elevator. Fourth would be rudder. 5 alpha, 6 beta. and then 7 for the rates. All right, I think that's looking pretty good. So let's go ahead and Control A, Control G. Delete all the extra wires out here. So now we have our basically our full aerodynamics subsystem. So this is going to be Aero. All right. So the 6-off input is going to expect vectors for the forces and moments. So I'm going to go ahead and mux up the 3 forces along with the 3 moments. Okay. Then we're going to put in wind angles 6-off or 6-off wind right here. And you'll see a lot of inputs and outputs, a lot of stuff to set up here. But we're going to go ahead and use our moments and forces from the aerodynamics. You know, maybe I need to make this a little bit bigger. That might help us out. All right. Okay, so that looks pretty good. So if we go, let's open up this 6-off block, change some settings. I'm going to change it to English. Keep the mass type fixed. And then just like before, I'm going to start it off 100 feet in the air, so -100 for Z. We're going to give it initial velocity V0, and then an initial angle of attack alpha 0, converting from degrees to radians. We'll always start at 0 beta. Start at 0 flight path angle, 0 bank angle. No, sorry, not 0 flight path angle. So 0 bank angle, that's the first one. Degderad gamma 0 for our initial flight path angle. And then we'll start at a 0 heading angle. Body rates will all start 0. The initial mass is going to be m. And then our inertia in the body axes is going to be, we're going to use diag to create a diagonal matrix and then pass a vector inside of it. It's going to be ixx, iyy, and then izz. So I know we don't have v0. So v0 is going to be 30, alpha 0. Let's set it to like 2 right now. And then gamma 0 will be like -5 maybe. So let's see if we have everything we need in the workspace. I think we do. We have mass defined? We do. Yeah. Alright, so that's looking good. There's one other force we have to take into account, and that's gravitational force. So in the 3-off block, it has an internal signal to generate gravity, or the force due to gravity. But in the 6-off version, we have to create that for ourselves. So I'm just going to go ahead and preemptively add a summing block here. Plus pipe, I think will get you, yeah, that'll get you that. And then, you know, we're going to have to add in, I'm going to make this a little bit smaller, we're going to have to add in our own gravitational force in here as well. So I know it's going to come from over here, so what I'm going to do to generate this, we're going to have an expression for gravity, and we're going to take that, the inertial expression, we're going to rotate into the body frame, because these have to be in the oh, actually we need to rotate it into the stability axes. So I know I'm going to have some sort of DCM that's going to take me from inertial to stability axes. So I'm going to go ahead and do a product here. It's going to be a matrix. Go ahead and invert that. Control I to invert it like that. The output is going to be our stability axes. I guess really it should be wind axes. Let me look up the function reference real quick to see what it needs to be. So if we right click, help, I think it's wind axes now. If we go to inputs, yeah, so the forces need to be in the wind axes. Okay. So this DCM is gonna have to take me from basically inertial to wind axes. Whatever that DCM is going to be multiplied. I've got a constant here. It's going to be 0, 0, mg. Should be your gravitational force. And I go ahead and Control I to invert that. And we'll hook that up here. So we're going to have some DCM. It's going to take this force, rotate it into the wind axes. It's going to be added with our aerodynamic forces, and then go into the 6-off block. And you know, one thing that we're not quite doing exactly right here is, since the inputs, the force inputs are expected to be in the wind axes, we're actually using, since we're using CY, that's in the stability axes, we'd want to use the crosswind force to be a little bit more precise, but we're always pretty much operating around 0 beta, for the most part at least. So I think this will be okay. Yeah. Do we want to do one more rotation? I think it'll be fine. Okay, so let's go ahead and let's set up some inputs. So I know I'm gonna have to have an input for the elevator. I know I'm gonna have to have an input for the rudder. Alpha, beta, that's gonna come from here. They need to be in degrees, so I'm gonna look for a radians to degrees block. And I'm gonna demux that. Oops. Alright. So this is alpha and beta. This is elevator and rudder. I want to log all of these. Let's also pull out our body rates as well. We have another radians degrees block over here. It's going to hook up to omega b, which is our body rates. And I know that I'm going to want those to be outputs, or at least Q to be an output. So I'm going to demux this. 3 outputs. I'd like to log all of them. So I'm going to do a terminator. The first one's going to be P, and then Q, then R. So I'm going to terminate P and R, and do an out for Q. This is Q, P, R. Let's log those. And then I need to feedback my rates in degrees per second, which would be the signal there. All right, I think that's coming along good. We're not going to need the these last 2 signals here. Angular acceleration, don't really care about, and the body acceleration, I don't really care about that one either. Same thing with the angle of attack and side-step angle rates. Inertial velocity. Let's see. Let's also, I think, so this output here, I'm going to double check this DCMWE. I think this is going to be DCM that takes us from inertial to wind axis. So I'm just going to go to help and verify that as one of the outputs. Yeah, so that's good. So we can actually use that to drive our gravity signal. What else do we need? We need our velocity. So we can pull that, do wind velocity. Oh, I hooked the wrong thing. This should go to the DCM, not the velocity. There we go. You know, actually, since this one's a little bit higher, I'm gonna throw the terminator on this one, because all we really care about is the scalar. So use a dot product. And a square root. So now we've got our velocity input. We also need our altitude input, so let's grab a selector. That's going to be hooked up to the inertial position. Right there. We only want the third one, the third element, and we need to change the sign since it's positive down. This is going to drive altitude. Oops, I'll log this signal as well. Okay, can we still compile? We can still compile, that's good. We've got velocity, altitude, elevator, rudder, alpha, beta, body rates. What else do we need? We also need phi, theta, psi. We need our Euler angles because those are going to get used as used in our feedback. So what are we going to do about that? Well, we know some of the information we have. We have alpha, beta, and we have the DCM to go from inertial to wind axes. So we can also build a DCM to go from wind axes to body axes based off of alpha, beta. Let's do that. So if you type in DCM, body to wind, second one, direction cosine matrix, body to wind. So this is going to build a body to wind DCM based off of alpha, beta. But we don't want body to wind, we want wind to body. So I'm going to do a transpose, or I think it's math function. And then if you double click, change the function to transpose. Okay. So now this is going to be wind to body. And we also need to go inertial to wind. So the first thing we need to do is go inertial to wind and then wind to body. So that's going to be, I'll do a matrix multiplication here. It's going to have to look like this. So you're going to have to make sure that you have the order here because the order affects what you're actually looking at. Let me double check this. Yeah, all right. So now we have this DCM that goes inertial to body. We're gonna run, there's a direction cosine matrix to rotation angles function. We can hook that up, hook up the output. It's gonna give us the output in radians, so we wanna go radians to degrees. And the first output is actually going to be your yaw angle because the Euler rotation order goes yaw, pitch, roll. So the first output's going to be yaw, and then pitch, and then roll. So let's demux these. 3 outputs. This is going to be psi, theta, phi. And we got a lot of stuff going on here, so I'm just going to combine these into a single subsystem. Alright. Call it Euler angles. Then the first input was the inertial to wind axis DCM, CE to W. And then the second one was alpha beta. I suppose we can avoid this line crossing like so. Then it's going to give us phi theta psi in degrees, or psi theta phi in this case. So psi theta phi. And let's log those signals as well. And then we can start this. So I'll get them selected and then stream to the data inspector. What else were we missing? I think we're doing pretty good. So I'm going to go ahead and save this and make sure it will compile with Control D. That all looks pretty good. So, let me see what this warning is. Oh. And we can hook up this guy to a terminator and then that should get rid of all of our warnings. So I'm going to go ahead, I'm just going to run this open loop for like 5 seconds and see what happens. And let's overwrite this run. Again, if you don't have this, this particular number of plot sort of subgrids, you can go to Format, Subplots, and I'm doing a 4x3. Newer versions of Simulink and MATLAB, you've got a little bit different user interface, but it should be pretty straightforward to figure out. So I'm going to plot, the first thing I'm going to plot is going to be the Euler angles. So this is going to be theta, and then phi, and psi. And then the rates, Q, P, R. Control surfaces, we'll say elevator and rudder. And let's do angle of attack down here. Side slip angle. And then how about velocity and altitude? So this should give us a good idea of what's going on with all the states of the vehicle. What I want to do next is linearize the model and compare where the system poles are that we get out of Simulink with what XFLR predicts. So I'm going to minimize that. Let's go to analysis, controls, design, linear analysis. And we'll do a pole zero map. Now, the same problem last time. So under analysis IOs, we have to say that, hey, we want to look at the whole model. So the root level inputs and outputs. And let's see where everything is. There's a lot of stuff going on. Let's check the longitudinal modes first. So this one looks like it's going to be our short period. And this is a 0.85 damping ratio and 26.5 radians per second. So 26.5 divided by 2 times pi will be around 4.2 hertz, 0.9 damping ratio. Let's go to the longitudinal modes. Yep, around 4-ish hertz, 4.5 hertz, and a 0.89. That looks good. So the phugoid we expected to be around 0.1 for the frequency and also 0.1 damping ratio. We're seeing here, if I zoom in, so we've got 0.17 damping. It's a little bit different, but it's still pretty low, probably within the realm of okay. And then a 0.64 frequency. So if we do 0.64, should be around 0.1 for the frequency, 0.1 hertz. So what Simulink has given you is the value in radians per second. So you divide that by 2 pi to get the value in hertz. So let's check the lateral modes now. First one's going to be our roll subsidence. It's giving us a 0.017 time constant. If we do 1 over that, divided by 0.017, that should be around 58 radians per second. Which that's going to be our pretty fast pull out here, which is around 50. So, you know, not exact, but not completely out to lunch. And let's see, these two should be our Dutch roll. So this is going to be around 0.4 damping and 10 radians per second. So 10 divided by 2 times pi. So that's 1.6-ish hertz and a 0.4 damping ratio. So around 1.6 and 0.4. Actually, it's this one that we'd be looking at, so but still pretty close. 0.41, sorry. And then the spiral mode, this one's really slow. So this is a 5.3-ish time constant. 1 over the time constant for first order systems is going to give you the natural frequency. So that's 0.18 radians per second. So if we zoom in way over here, that'd be this guy. So 0.2, not too far off. So I think we did pretty good. You know, it doesn't match exactly because there's some, I mentioned this in the last video too, but there's some stuff in XFLR, some additional coupling that's being considered in developing the linear model that we're not modeling in Simulink. But I think this will be good enough for the controller design. Or we'll see, I guess, you know. Who knows what's going to happen. But this should give you at least a good baseline. And then if you need to do some additional tuning based off of your test flights, you can do that as well. So the linear model looks good. I'm going to close this. Plant model looks good. So now we're going to do the actual controller architecture. So let's go ahead and I'm going to Control A again, Control G to make that all just one big subsystem. I'm going to have to relog my inputs, the elevator rudder inputs. So this is elevator, rudder, stream those. Okay. Probably make this collapse this a little bit to get it to display a little bit nicer on the screen. Move that. Move this down a little bit and this down as well. And then we can probably move this up some. And this up and this up. There we go. So hopefully that's maybe a little bit easier to read. I don't know. Okay. And then this now becomes our plant model. So let's adjust the order here. Let's do Q and then theta. That way when we wrap it, it'll look prettier. So I'm going to change theta to be the second output. Okay, I'm just checking to make sure we're outputting these in degrees. So we know that's in degrees, and then our rates are in degrees as well. So I'm also going to throw back in that second order nonlinear actuator model. And I think this was, I don't even remember. I'm going to have to go back and open up the model we did last time to see what we set it at. I'm just going to copy it actually. All right. So we'll do one for the elevator and one for the rudder. And then we're going to have an inner pitch rate loop. This is going to be a PI controller. And you know, we could just take our settings from before. I'm actually going to see if we can actually tune it from within this model. Should be able to. Let's see. Maybe not. Why would it be having trouble? It might be because we would be trying to tune it without a feedback loop. That would be a problem. Okay. Oh man. This is going to be minus plus, and then the pipe character. It's always a game to see if you can get the inputs here right to get the configuration you want. So that's what we want. And let's try that again. Okay. So we probably want a little bit faster than 18 times 10 to the 5. All right. And let's see if we can get this to where, similar to kind of the response we had before, I think what we were just shooting for was we didn't want a whole lot of ringing. So probably something around like that would be okay. And I'm guessing this is going to be a very similar value to what we had previously. And then we're going to do an outer pitch angle PI. Create another feedback loop to our pitch angle. We'll tune this guy. Yeah, somewhere around like that. So let's also look, just like we did before, let's look at what the margins and everything look like as well. So we can add an open loop Bodhi plot and a controller effort plot. Bring this one down here. So that's probably okay. That's not too much deflection. I don't know. Depending on what it looks like in the time domain response, we might need to slow this down a little bit. I don't know. We'll see. We'll play with it, see what happens. And then if we go here, characteristics, minimum stability margins, we should still be fine. 14.5, give or take a little bit, gain margin, and 60 degrees phase margin. So that looks pretty good. So I'm going to update the block, close this, and call it a day on the pitch design. And I'm guessing we have very similar values to what we had previously. We're going to drive this with a step command. This is going to be called pitch ref. I'll log this signal. And let's say at 5 seconds, let's go from our initial value of 0 down to -5. So we shouldn't be, what are we starting at? So we're starting actually pretty close to close-ish to -5. So it should track to -5, or no, I'm sorry, it should track up to 0 and then down to -5. So if we go ahead and run this, we need to run it for 10 seconds. See our pitch angle here tracks up to 0 and then down to -5. I'm also going to display the pitch reference so we can see that. Pitch rate, elevator, and angle of attack, those all look pretty clean. So I think that's pretty good. Now we just need to go and do the lateral design. So what I'm going to do is I'm going to have a PI controller that is going to track our roll angle and drive the rudder. This is going to be a roll angle PI. So we'll hook this up to phi, so roll angle. Let's go ahead and tune this one. And even though the response looks pretty good here, the problem is it's pretty slow. So I'm going to see how fast I can get it before it starts to misbehave. Maybe around there. Let's look and see what the margins look like. .3 dB, 60 degrees, and then I'm going to look at the controller effort as well here. So you can kind of see as we increase the gain, this curve shifts up, which reduces our gain margin. and then where that crossover is moves on the phase curve. So you can imagine I'm getting pretty oscillatory here, really low margin, and if I just kept cranking it, eventually, you know, we cross over this point and become unstable. So I'm gonna stick with right around there maybe, and you know, we'll see. It's probably not going to be the cleanest response for our heading tracking, just because we don't have a dedicated rudder and ailerons. We're relying on that rudder to induce some side slip, to induce a rolling moment, to change our roll attitude, and then that change in roll attitude to move where our lift vector is pointing, which is going to give us some acceleration towards the center of that turn us. So let's go with this and see what our outer heading or our yaw angle loop looks like with the center loop. So then I'm going to have an outer yaw angle PI. Oops. And that's going to track our yaw angle, psi. And let's see. Oof. Yikes. Let's try getting rid of that integrator. I think that might give us a little better performance. We might not want to have the integrator out here inducing that phase lag at kind of that lower frequency. So this is better. It's not the cleanest response in the world, not by a long shot, but at least it makes it there, and it doesn't look too oscillatory. You can kind of see this initial jump here. You know, this is really due to the fact that you're moving the rudder and you're creating that yawing moment. So you got that initial turn, do the yawing moment, and then you create side slip, which manifests itself in changing a roll attitude, and then the rest of it, kind of the slower response here, is that change in yaw angle you get just from the fact that you're turning. So that's kind of why you have this sort of, you know, multimodal step response going on here. So I'm going to add the same plots as before. Look at my minimum stability margins and the controller effort. Yeah, it's not the prettiest thing in the world, but it seems to kind of be doing what it should be doing. I'm going to slow it down a little bit. Let's see. Maybe somewhere around there. So, you know, it takes about 3 seconds to get to about 95% of the command. It's probably okay. Update the block. Hit OK. Then, tell you what, let's create another step here. It's going to be called ref yaw. Log that. And then we're going to leave this at 0 for right now. So the final value is going to be 0. Let's run the simulation again. And then now we should have some tracking on our heading, on our yaw angle right here, the psi. And then we still have that good pitch tracking. And what we can do, let's lengthen this, and let's say I'm going to change the pitch set point to around, I guess I'll leave it at 5. And we'll at 10 seconds we're going to put in like a 5 degree, maybe like a 10 degree change in yaw angle, and let's see what happens. So at 10 seconds I'm going to go from 0 to 10 degrees, and let's lengthen this out to at least 15 seconds. Let's see what happens. And then on psi, I'm also going to display my reference for yaw. And let's try 20. So we can really see what's going on. Okay. So initially we're at around -5 degree pitch angle. We go up to 0. That causes us to slow down. Then we go down to around -5. That gets us back up to maybe around 30 to 33. And then at 10 seconds, we command a step change in our heading reference, or our yaw angle reference. We go from 0 to 10, You can kind of see, just like what we were seeing in the linear response, you have this kind of initial movement and then a slower response after that. So I think this should be pretty good, because you shouldn't really have to regulate too much for the yaw disturbance. So all of these should still be pretty small signals overall through most of the flight, but you still need to have some sort of control to get rid of any disturbances you see. So I think this looks pretty good for now. You can always continue to play with it and do some sensitivity analyses to see if you're flying at different velocities, or you have smaller, larger changes. Maybe you have a coupled response in pitch and yaw. See what the responses look like there, and then you might need to adjust the gains as well. And the other big thing I want to stress here is that this design is only going to be as good as your model is. So if you have a model that you're working with in XFLR that's not representative of reality, then no matter how robust your controller is here, you're not going to get the performance that you would see out of the simulation. So I think it'd be valuable if you have the ability to try to run some CFD and see if how those responses compare. How do your error coefficients compare with what you're getting out of XFLR? So I think that'd be a good thing to see at the CDR if you guys are able to do that. And then so I don't know how long this ended up being. Let's see. Okay, an hour and 15. So that's not too bad. I must have gone a lot faster than when we did the original pitch autopilot design. But you can see we went through the full process, building up the 6DOF model, and then tuning each of the loops independently. First the inner loop and then the outer loop. So yeah, that's not all that different than what you do in industry. It's certainly more complicated on commercial aviation, defense systems. The dynamics are a lot more complicated, but sort of the general process a lot of times is very similar. So good luck. I look forward to seeing what you guys come up with. And if you have any questions, feel free to send me an email, and I'll try to answer as best as I can.